Hey, what's up, folks? Today we are going to be looking at our next topic. Though it says binary numbers, Unit 2.2, it's technically not binary numbers. It has to do with data and imaging processing. And we're going to go through and kind of understand exactly, what this is about and what it means. So when it comes to image processing, or in other words, compression, all right, it's a technique that is used, algorithms in computer science that is used in order to conserve data, conserve space, compress information down so that information isn't as extensive. As you know, with devices that we have finite amount of space. Our phones tend to have, 64 to 128 gigabits of space, and once we run out of that space, all right, then there's nothing we can do about it. We either have to transfer items off the phone or we have to delete information out. So early on in the concept of this topic, all right, there were two main types of compression algorithms, and we're going to be discussing them within this section here. All right, but again, all of this data, and as we've kind of really hammered on for the past couple of for the last unit and somewhat into this one, is about the binary code and how basically data is broken down into bits of information. All right, so we have, data bits, ones, which will represent something within our image, and then we have zeros, which is going to represent the exact opposite. Now, depending on the type of image algorithm or protocol that we're using, it will mean slightly something different. All right, so to understand this process, all right, we have to understand binary code and how the bits work. All right, because that is then going to allow us to understand how the digital imaging is going to be, and how this digital imaging is basically another key feature of abstraction, which again, as we've been talking about quite often now, abstraction is a very big part within computer science. All right, so one of the first types of image processing techniques or representations that was discussed or talked about was called or titled run length encoding. All right, so run length encoding is a form of lossless image compression. And what I mean by lossless image compression, as you can see with the fourth bullet down, it gives you more of a definitive definition. But it means that every bit is accounted for. So if you had a picture of a tree, or in the next slide you'll see a rocket ship, each pixel is going to be encoded with a bit of data. All right, so based on, if we're looking at just a very standard black and white example, if the color is white, we'll call it a data bit of a 1. If the color is black, we'll call it a data bit of a 0. All right, so again, because we want to think from a binary code standpoint. All right, so lossless compression then refers to that as we take the image and we break it down into its data, every single pixel is accounted for, whether it be a 1 or a 0. All right, so when we have to then compress, when we have to compile, put the image back together again, well, then we need to account for every single 1 and every single 0 that was compressed or taken apart, if you will, so that when we put the image back together, we're going to have the same exact image once again. This is different from what's called a lossy technique or lossy compression algorithm. And that's something that, as you can see here, what a JPEG uses. And if you have a digital camera, most digital cameras take their photo files, when they save them, are in JPEG format. And the JPEG is just another type of imaging format. But the main difference between these two is that where in lossless compression, every single bit of data is accounted for, but within a JPEG format system, because of the fact that our eyes are not sensitive enough to determine slight variations between certain shades of color, let's just say like the color blue, you have maybe like a powder blue versus a sky blue. They are very, very similar in color. And if you put the two colors side by side and take a step back a certain amount of distance, your eyes might not be able to discern or to tell the difference between the two. They might just look light blue to you. And so with that in mind, what the JPEG standard does, it will actually look at all the pixels in the photo, and it will look for certain regions where the color variations differ but are so close to being exact that they will delete out certain bits of data and will sort of kind of wash over that area with the same color pixelation. And what that allows the system to do is to cut out bits of data, and when it compresses the folder or the file, what it will do is it will compress the file down maybe 20%, maybe even up to 50% its original size. So if you have a digital camera and you snap a picture at, say, 20 megabits, and it's in JPEG format, and depending on the resolution you are using, it might actually save that picture at maybe 12 megabits in size. All right, and the reason it's done that, as I've said, is that it will actually go through the image and will smartly cut out coloration that is very similar, that we as people can't discern the difference between. All right, the downside with that, though, is that when you're now removing bits of information from a picture, if for whatever reason you wanted to get it back to the original raw format, you're not going to be able to do that, because once the data is removed or taken out, you no longer have the ability to put it back again. Unlike lossless, where in a lossless compression, since every bit of data was accounted for, when you compress it, after you expand it back out, all right, you will have all those bits of data available to you. And so as the example is showing you over here, when medical imaging, whether it be a scan of the human body or just a scan of some paperwork or whatever the case may be, you want to make sure that every single bit of detail is present, so that if you have to uncompress a file and bring it back to its original format, you want to make sure that all the data is there. Because if, God forbid, if a doctor is looking at a chart or a scan, an X-ray, an MRI, whatever, you want to make sure that all the data is present when they're looking at it, instead of them seeing maybe like a gaping hole somewhere, and that's the area that they were looking at, and they can't even tell if, you know, your organs or your system is working fine, or if, God forbid, there's something wrong. So big difference between the two. And they have, you know, like I said, pluses and minuses behind each format. All right, so looking at the run length encoding, as I said with the rocket ship example, it basically works off of, you know, back in when this was originally, the inception was created, everything was based off of a monochrome system, basically meaning two colors. The only colors that they used within a computer system was black and white. And, you know, you were able to then detect, or you were able to create images or text or what have you based on using this monochrome system. So they refer to that as 2-bit encryption. All right, I'm not 2-bit encryption, I'm sorry, a 2-bit, basically just a 2-bit color chromatic scheme. So when we look at the diagram in the top right-hand corner over here, all right, we see a rocket ship. And what we see in the background is we see a grid, all right? And if it's kind of hard to see, but if you were to really, really zoom in, you would see basically a grid of 16 squares going down and 16 squares going across. All right, so if you were to count up or just multiply the two numbers, you know, you would get basically a grid that would consist of 256 blocks. Those blocks would basically count like the same as a pixel. All right, so each block is a pixel. All right, so with that being said, if you were to look at all the numbers over here, the way how we would read this is that if I look at the number 16, the way how the RLE compression would work is that there would be some assumptions that were made over here. The first thing is that the first number that you see is the number of blocks that is in row number 1 that would be considered the color white. All right, we go down the next line here. We have the number 12. Well, that would mean that the first 12 blocks would be white. Once we hit a comma, what we're then assuming is that the next run of numbers would be black in color. So whenever we see a comma that's separating any number, all right, it's telling us that the first color is white, and therefore that is the run of numbers that there need to be white pixels or white blocks. The next number would be black. The number after that would be white, all right? And then we just keep chaining black, white, black, white, black, white as we went through the entire pattern over here. All right, so when we go all the way down to the bottom here, we see we have one white pixel, followed by two black pixels, followed by one white pixel, by one black pixel, three white pixels, one black pixel, 7 white pixels. All right, and then when we follow that, we basically get the shaded in pixels that we have, giving us the pattern that we see. But if we count up all these numbers over here, we should see that we have a total of 62 numbers. All right, so the largest number being 16. And that's because it matches the grid. When the grid would get bigger, that number would obviously increase as well. All right, so if we were to use the 8-bit number system, and this goes back to your binary code, where we have 8 bits that make up a byte. All right, there's your binary numbers, the string of zeros and ones, 8 spaces worth of them. All right, so if we use that as our number system to determine the number of pixels, basically what we are doing is we are taking the number 62, which is the number of the amount of numbers that we have over here, which make up our image, and we're multiplying that by the 8 bits, and again, the 8 bits that make up each specific number. And what we get is we get a value of 496. Well, because of the fact that if I look at the number of squares here, and if I assume that every block there is 1 pixel per block, all right, well, that would mean, since I have 256 squares, that means I would have 256 pixels of data, or 256 bits of data, because we can say that 1 bit of data takes up each pixel here. So 256 pixels would be the amount of data needed just in general if I used a monochromatic system. But if I use the 8-bit number system, all right, I would end up needing 496 bits of data to represent this image. And so from that perspective, it's not a good compression algorithm, because we're using more memory than what I would have needed if I used just a standard monochromatic system. All right, so that's basically what that is referring to when we look at monochrome images. But as you know, we don't use a monochromatic system. All right, we use colors. All right, but to kind of make sense of that monochromatic system, like I mentioned, all right, if you were to replace the picture of the rocket with 1s being the color white and 0 being the color black, and we'd fill the binary data in like we would as a color, you still would see the rocket pattern that is within your system over here. All right, and so that's why the compression algorithm for RLE and using monochromatic images is not a good thing. Okay, but like I was starting to say, when we now get into color images, it's a different ballgame. All right, so the next big breakthrough when it came to imaging was when we got out of the monochromatic colors and we actually started getting into the standard 8-bit color system. And then from 8-bit it went to 16-bit, and currently it's up to 24-bit right now. All right, so what that means is with an 8-bit color system, we have the ability now, again, using 2, which is our binary code of zeros and ones, but 2 to the 8th power of amounts of color. And so if we were to take 2 to the 8th power, we'd get a total of 256 colors. All right, so the original 8-bit color system allowed us to choose between a variation of 256 blends of color, with obviously your most primary and secondary colors, and then specific shades in between those colors. All right, and so what we see over here in this little color palette is an example of, you got your black color in the top left here, you got your white color in the bottom right here, and you see a variation of shades of yellows, oranges, and reds as they get darker and lighter, blues and greens and purples, and so on and so forth. All right, and so this color palette is used by a mixing of reds, greens, and blue color. All right, and because we're using binary code, 8 bits of data, we're basically resigning 3 bits of data for the red color, 3 bits for the green, and 2 bits for the blue. All right, and the scheme that we use will look something like this. But remember, binary code isn't 1 through 7, 0 through 7. It would basically be an array of 1s and 0s as we go through. These are just basically showing us the column number that the red, green, and blue values are in. But for those of you who actually ever used a paint shop program or Photoshop or anything like that, you would notice that when you take your eyedropper and you mouse over a color, the program actually allows you to get the red, green, and the blue values. And it will give you a number anywhere between 0 and 255. All right, that'll give you a total of 256 numbers, but again, we're not starting the count at 1, we're starting the count at 0. So 0 to 255, and then a mixture of 0 to 255 for red, for green, and for blue will ultimately provide us the specific color. So, so when it comes to that, what we do now, if we apply that logic now into the rocket ship example and how run length encoding works by applying the 8-bit color scheme, okay, what we get is something, well, it'll be on the next slide. But recapping, we have 16 again on the top number would tell us, we're assuming that that is going to be what's going on here? That is going to be the value that we assume to be white in color. And then the next line we have 12, and we have 12 we're assuming is the color white. 3 is the color black, and 1 is the color white. All right, so what happens now if we apply this new 8-bit color scheme into the process? All right, well, what we're going to do now is we're going to assume that the number 255 is white, and we're going to assume that the number 0 is black, and then any number in between there would be a variation of shades of grays and reds and greens and blues and orange and yellow and purple and so on and so forth. So rather than having the number system, as you saw on the previous page, look like 16, 12, 3, 1, right? What we're going to see now, as you see on the left-hand side over here, is we're going to see, we're going to see instead of 16, we're going to see the number 255, which counts as white, 16. The number 16 letting you know the run of how many white blocks do I need. Followed by the next, which we have 12, all right, and that would then be 255, 12. So let me actually write the 255 first. Okay, 255, 12. So that again tells me the color and then the run of how many white blocks I need. I'm going to separate this by another comma, and then I'm going to write 0, 3. The 0, the first number, always tells you the color, and so therefore the 0 is black. And then the next number tells me the run of how many black blocks do I need. I'll separate that group by a comma, and then we have again 255, 1, the first number, 255, telling me the color, which is white. And then the second number tells me the run of how many white blocks do I need. All right, so this is the alternating scheme that we would see now. Well, because we're adding an additional number, remember, for the previous example, we only use 62 numbers to represent that monochromatic image. And those 62 numbers, let me just kind of go back, really quickly. Those 62 numbers were the number 16, 12, 3, 1, 10, 5, 1, etc., on that side. Well, now because we are putting an additional number in front of those numbers, we've gone now from 64 numbers, we've doubled it up to 128. All right, so we now have double the numbers that we're using. And if we still are using that 8-bit number system, all right, if we multiply 128 by 8, we get a total of 992 bits of information that we would need in order to produce that picture. Well, if we're using a true 8-bit number system, all right, so for the colors, all right, and because we have a total of 256 blocks available to us, if I multiply the two numbers together, what I get is a value of 248. So that tells me that in order to represent this image from an RLE perspective, all right, using the traditional method, I would need a total of 2,048 bits in order to represent or replicate that image. But using the 8-bit color system, all right, I only need a total of 992 bits. So what this shows me is that the amount of compression that is happening when I'm using the 8-bit color system to represent that image is over 50%. compared to if I used the standard RLE encryption that I started with the monochromatic system. So what we see in this aspect is the data that we're saving, or the amount of space we're saving, is huge compared to the monochromatic system, which unfortunately didn't allow us to save any space or information. All right, so let's move on to the next slide. So what we're using now is we're using current standard is a 24-bit color system. All right, and we're still using the standard binary code, 8 bits for colored images. Right, but what we're doing now is we're using the 24-bit technique. So we're using 8 bits per red, 8 bits for green, 8 bits for blue, which yields 8 plus 8 plus 8, giving us those 24 bits of data information. 24 bits of data information, and unfortunately I think there's a typo. Yeah, so in the typo here it says 224. That shouldn't be 224. This should be 2 to the power of 24. All right, and so if we were to take the number 2 and raise that to the power of 24, what we would find is that we would have the number 16,777,000 and change. And that tells us the level or the amount of colors that we can have available to us whenever we do our photography or artwork or whatever. That number, as I was mentioning earlier, that number by no means is the human eye allowed to be able to discern the difference between the shades of color. All right, because there's way more colors than our eyes can distinguish. And that's why when I said earlier about the JPEG format, the lossy compression, is that the system can sacrifice bits of data and our eyes will still be able to see the picture for what it is, and we won't be able to see glaring holes or data lost or anything like that. And that's why the JPEG system uses this compression algorithm in order to save memory, save space, and therefore you can fit more information on your device. And I pardon for the interruption, but I'm at my school right now, and they're unfortunately going to be making some announcements. So hopefully I can get this done before the next one. All right, so with that being said, rather than using just the number 255 or 0 or any number in between to dictate the color black or white or anything in between, we're using those 3 bits, or the 8 bits, I should say, 3 times over for each color. So in order to make the color white, right, in the old system we used 255. Well, now what we see over here is we're using the 8-bit system in the 24-bit color scheme. So we're using the number 255, 255, 255, and that would obviously be the new representation, which would give us the color white. Where to represent the color black, rather than just a single digit of 0, we're going to be using 0, 0, 0. And that will let us know in that color scheme that is the color black that we're dealing with. All right, so what does that look like now as far as the rocket ship problem? Well, rather than just having that number 16 or having the 255, 16, we now have to use a new 24-bit system with a format, which we're now placing 255, 255, 255 in parentheses, and then 16. So this string, again, of 255s is letting us know what the color is, while the next digit lets us know the run of how many numbers of that color we need. The next example, if you remember, we only started with 12, 3, and 1, because we assumed white, black, white alternating. And then it turned into just 255, 12, 0, 3, and 255, 1, again, to represent the color and then the run of numbers. Well, now we are using all 3 bits of data to represent the color, followed by the number, which is letting us know the run. All right, and so when we look at this from a compression algorithm, what we have is rather than having one set of numbers or 2 set of numbers like in the previous problems, we have a total of 4 sets of numbers. So what we're doing is, so for the number 62, is if that was the number of the amount of numbers we were starting with, rather than using 62, well, we're multiplying that value by 4. And so we have a total access, or we're using a total of 248 numbers in order to represent the color and the run of the pixelation. So if we multiply those 2 values together, within our 8-bit system, 62 times 4 gives us 248. All right, and then 248 multiplied by the 8-bit binary number system that we're using gives us a total of 1,984 bits of data that we're using. Well, again, going back to the original explanation, we have a total of 256 pixels or boxes on our image, and this time we're using a 24-bit pixel coloration. So if we multiply 24 by 256, that is going to give us a total number of 6,144 bits. So by using this compression algorithm and using the number system that we have up here, we're only required to use a total of 1,984 bits instead of using the 6,000 plus bits of data if we would just use the standard RLE compression algorithm. And so what that lets us know is that we have now an absolute major compression going on of about 70%. And then that 70% compression means that we are able to fit much, much more data on our device because most of that data is being compressed, and therefore we can add more photos, add more audio, video, etc. Into our computers, into our phones, tablets, etc. All right, so that means that the compression algorithm that this uses is actually really, really good. So saving a lot of memory. All right, so that pretty much sums up the using binary and also compression algorithms, why they are extremely important, how it has evolved from the past using the monochromatic system up to currently using the 24-bit system that we are using. So hopefully moving forward you can kind of see how the binary data and bits of data are extremely important when it comes to these concepts, because ultimately, and it's going to seem like we're, I'm kind of beating a dead horse here, but, it really comes back down to the binary data, the bits of data, and how the computer system will read the binary code moving forward. So I'm going to pause for right there or stop right there. There's going to be a follow-up video that is going to talk about what's called parity bit, and that's when we send data or information and how we can prevent data from being corrupted. So aside from that, have a great day. We will talk to you all soon. Take care.